So, have you ever stopped and wondered how we even get our heads around things that are just impossibly big? I mean, from giant machines to entire continents. Today, we're going to dive into this simple but really powerful mathematical trick that lets us shrink the world down to a size we can actually work with. Okay, so let's start with something familiar, but, big. A 747 jumbo jet. It's around 70 meters long. You can picture it, sure, but there's no way you're fitting that on a piece of paper, right? We need a way to represent it perfectly, just a whole lot smaller. Now let's zoom way out. This is a map of Victoria Island, way up in the Canadian Arctic. We just went from a 70-meter jet to a piece of land that's hundreds of kilometers across. So you can see how the challenge of representing it just got a lot bigger. And for our final leap in scale, how about our solar system? We're talking planets that are thousands and thousands of kilometers wide, separated by millions more. I mean, seriously, how on earth do you even begin to draw a picture of that? And that, right there, is the central question. How do we take these absolutely massive objects and territories and shrink them down into something we can actually manage, like a blueprint, a map, or a model, without messing up their perfect proportions? Well, the answer lies in one simple, super elegant concept. It's like a secret code that unlocks our ability to shrink the world. Let's call it the magic number, the scale factor. First things first, a key term you gotta know. When we create a scale diagram that's smaller than the real thing, it's called a reduction. Makes sense, right? A map is just a reduction of a huge piece of land. A little toy car is a reduction of a real car. And here is the hero of our story, the scale factor. It's simply the ratio that compares a measurement on your small drawing to the exact same measurement on the big, real-life object. It is the mathematical heart and soul of every single reduction. And check out how simple this is. The formula is just a fraction. You just take the length on your small diagram and divide it by the length of that same part on the original object. That's it. That's your scale factor. And here is the golden rule. For any reduction, anytime you're making something smaller, the scale factor will always be a number less than 1. It could be 0.5, 0.1, or even 0.0002, but it'll never be 1 or more. That's your clue that you're shrinking something down. Now, you're going to see scale factors written in a couple of ways. Sometimes it's a ratio, like 1 to 50, which just means 1 unit on the drawing equals 50 of those same units in real life, or you might see it as a decimal, like 0.02. And here's the thing. They mean the exact same thing. 1 divided by 50 is 0.02. It's just two different ways of saying the same thing. All right, enough theory, right? Let's get our hands dirty and see how this magic number actually works in practice. We're going to take an object and shrink it, step by step. So here's our mission. We've got this octagon, and we want to create a perfect, smaller copy of it. Our instructions are crystal clear. Use a scale factor of 0.25. Let's see how it's done. So how do we actually pull this off? It's a super simple 4-step process. First, you measure a side on the original, let's say it's 4 centimeters. Second, you grab your scale factor, which we know is 0.25. Third, you just multiply them together. So 4 times 0.25 gives you 1 centimeter. And finally, you just draw your new smaller side. Do that for every side, and you're done. Perfect reduction. So that octagon example is great for getting the mechanics down. But where does this stuff show up outside of a textbook? The answer is, well, it's literally everywhere. Let's look at a couple of real-world examples. Okay, check this out. A classic engineering problem. We have a scale diagram of a truck. The scale is 1 to 50. Now we know that on the actual truck, the wheels are 3.85 meters apart. So the question is, how far apart should they be on our drawing? Remember that ratio format we just talked about? Well, here it is in action. A scale of 1 to 50 means that every single centimeter you measure on this paper represents 50 whole centimeters on the real truck. It's the one consistent rule for the entire drawing. Okay, let's break down the calculation. We just apply our formula. The scale factor, which is 1 divided by 50, gets multiplied by the real distance of 3.85 meters. That gives us 0.077 meters. Now that's kind of a weird number to measure with a ruler. So we just do a quick conversion and bam, it's 7.7 centimeters on our diagram. Perfect. Let's try one more. Here we've got a blueprint for an outdoor hockey rink. And you should notice the scale right away, 1 to 400. This tells us we're shrinking a much larger object, so our ratio has to be way smaller to fit it all on the page. So here's a quick challenge for you. A real hockey net is 1.82 meters wide. Using that 1 to 400 scale, how wide would you draw the net on this diagram? And guess what? You'd use the exact same math we just did for the truck. It's a universal tool. And there you have it. From jets to islands to hockey rinks, the very same principle applies. That scale factor, it's the bridge between the massive real world and the world we can draw, model, and design on a piece of paper. So let's just recap the big takeaways. A reduction is what makes huge things manageable. The secret sauce is the scale factor, our magic number, which for reductions is always less than 1. The formula couldn't be simpler. Diagram length divided by actual length. And this idea, it's used everywhere, from the maps on your phone to the blueprints for skyscrapers. And that really leaves us with a final, powerful thought. Every great creation, every skyscraper, every video game world, every amazing machine, it all started as a reduction, a small-scale plan. It's how we plan the impossible. So the real question is, now that you know the secret, what massive idea will you shrink down to size?